suppose that I have some function that I'm just going to call f of t. And I guess I can label it as like y equals f of t. That's how I'm getting my height, is this function of time. And that means that this axis right here is like the t axis. It's some function of time. And I want to find the area from t equals a to t equals x. Now, using our new definite integral notation, I can write that area. And I can write that area as saying, I'm going to have the integral of f of t, that's like my height function, times dt, that's my little bit of a base function. I'm adding these up from a to x. Now, something that's really important here is this area, the area itself, is a function of x. If I scoot x over, we have more area. If I scoot x this way, I have less area. So this whole thing is a function of x. I don't know what the function is, but I know that it's a function of x. Here's the part that really, for no reason at all other than we're trying to get to the fundamental theorem of calculus. Here's my y equals f of t. And I don't actually care about that area I shaded in over there. I really care about this area right here. And that area right there, this is x. And on this side, I'm going to call this x plus h. And if in your head, you're thinking, oh, wait, x plus h, that's got something to do with that word from 17a we did a lot, right? That is where we're going here. That x plus h maybe makes bells going off in your head. Oh, yeah, that's a derivative thing. Well, that area in there, if I think about it as this function, that area is f of x plus h minus f of x. Because that integral notation says that if I go from a all the way to x plus h, I have like that big area. And then if I subtracted off the red area that we had in there, I'd be left with just this little piece. Now, we're going to do that mathematician-y thing that we've done a few times this quarter, which is, sorry, I'm trying to like make sure I stay on the screen here. I think I'm doing okay. If you can't see what I'm writing on the screen, someone tell me before I go too far. Here's my a. Here's my x. Here's my x plus h. What I'm going to do is I'm going to do that mathematician thing we were doing before and say, oh, wait, I'm not finding the real area. I'm just going to make that a rectangle. Well, I know the area of this rectangle here, my base, is the distance between x and x plus h. So what's that width? Totally. And to get my height, because I drew it in as a left-hand endpoint, my height is going to come from plugging x into the function. So the area of this rectangle is actually h times this little f function evaluated at x. And now we're going to do that thing that we did so often in 16a, and that is, cool, that area is approximately like this thing. They're not equal, but they're approximately equal. So that rectangle area of h times f of x is approximately equal to this f of x plus h minus f of x. And if I wanted it to really, really be equal, I would just take the limit as h approaches 0. Rearranging this, and then taking that limit as h approaches 0 is what brings us back around to saying, oh, well, we know what that is. That is a derivative. That, folks, is part of the fundamental theorem of calculus. I do not believe you will ever have to prove this or walk through those steps, which is why I suggested not taking notes. Here's the big picture thing that is important and should be our takeaway here. If I write the integral from a to x of f of t dt, then this is some function of x, and the relationship here is that f prime of x is equal to little f of x, which means that is the antiderivative of that thing on the inside. And that gives us a tool to now evaluate those definite integrals and to find areas by using antiderivatives, not having to write out those Riemann sums, not having to find areas of rectangles, not having to approximate areas, but actually we have a relationship here that evaluating this integral is equivalent to finding the antiderivative. Now there's a second part to the fundamental theorem of calculus that really is just algebra. Would anyone like to see me do the algebra part, or you want to just believe me? Believe? Okay, so totally fine. We're just going to believe me. And if anyone wants to walk through the algebra, I walk through it in the handout in Canvas. The second part of this is that if I'm looking for the area from A to B of some function, all I have to do is find the antiderivative and then evaluate it at the rightmost endpoint and subtract off evaluating that antiderivative at the leftmost endpoint. So sort of two steps. I find the antiderivative. And then evaluate at the endpoints. Let's get a few practice problems with that. So get some practice. So if I write the integral from 1 to 5 of 2x minus 3 dx. First of all, this definite integral represents something. That definite integral, one thing that we could say that it represents is if I had the function y equals 2x minus 3. So let's see, y-intercept would be down here at -3, slope of positive 2x. So why did I give myself fractions? Are you guys okay if I switch my 3 to an 8? I just don't want fractions. Not this morning. Okay. So now that's a -8. And I know that the x-intercept is going to be at 4. So I can draw my picture in here. And this integral represents the area from 1 to 5. Now we could do that using geometry. They're both triangles. We could figure out what that area is. We could do it by writing a Riemann sum. We could do it by estimating with rectangles, or we can actually evaluate this using the fundamental theorem of calculus. Evaluate using, by the way, FTC is a very common abbreviation for the fundamental theorem of calculus. So let's evaluate using the fundamental theorem of calculus. So step 1, we need to find the antiderivative of 2x minus 8. So if I find the antiderivative of 2x minus 8, add 1 to the exponent, I'd have 2x squared, and then I'm dividing by 2. My 2's would cancel out. And then I'd have the antiderivative of minus 8 is going to give me minus 8x. Now there's something I'm not going to write down right now, and that's the plus c. That falls out of the algebra when I was saying, just trust me on this one in terms of the formula. We don't need to write the plus c if we have limits of integration or if we are looking at a definite integral like this. So we found the antiderivative, and step 2, we're going to evaluate at the endpoints. Wait at the endpoints. I'm going to pause just notationally for a second. The way that I would write my workout for this problem. Oh, that was not a -1. It was a +1. I don't know why I wrote -1. I'd be going 1 to 5, 2x minus 8 dx. And notationally, after I found that antiderivative, I would not write the integration symbol anymore. I would just write what we found for the antiderivative, the x squared minus 8x. And then instead of having that integration symbol in the front, I would put a vertical bar at the back and rewrite the numbers. And then I plug in the 5 and subtract off plugging in the 1. So I would have 5 squared minus 8 times 5, and then subtracting off 1 squared minus 8 times 1. By the way, just looking at the picture, do we expect our final answer to be positive or negative? So let's see what happens. So 5 squared, that's 25. 8 times 5 is 40. 1 minus 8 would give me a -7 in there. 25 minus 40, that's 15 minus -15 minus a minus will make that +7, and I get -8, which we were expecting a negative number. So great, we got a negative number. I'm going to do one more and then open it up to questions from the homework if there are any homework questions that you all would like to see me go through. Let's find the integral from 0 to pi. Why not? Of cosine 3x dx. Pick that up. So my first step is to find that antiderivative. and finding the antiderivative of cosine, I'm asking myself, whose derivative is equal to cosine? I heard whispers. I'm going to pretend everybody confidently said sine. So I would have sine of 3x divided by 3. Again, I'm dividing by that constant, sort of undoing that little chain rule piece of it. And I'm going to evaluate this from 0 to pi. So I would have, I would have sine of 3 pi over 3 minus sine of 0 all over 3. What's sine of 3 pi again? How about sine of 0? How about 0? Sine of 0 is 0. So this whole thing came out to be 0. If that is surprising, we could think about what that graph should look like. And it's not a regular cosine graph because of that 3x, and that changes the period, which means this ends at 2 pi over 3. Because the 3x means that I would fit 3 of them in a normal 1 period of cosine. So if this is 2 pi over 3, then we're not to pi yet. That's only at 2/3 of a pi. So I'd have to keep going. Now I would be at 4 pi over 3. So I went too far. And I may have gotten myself in deeper than I wanted to get. But I think halfway between 2 pi over 3 and 4 pi over 3 is 3 pi over 3. Which means we would be looking at this area. Tell the person next to you why it makes sense that we got 0 for the integral. Area above the curve, we give what kind of a sign? An area below the curve, we give what kind of a sign? So all of the areas above the curve have a corresponding exactly the same shape area below the curve, and they're all going to cancel out. Now, do I think that you need to be able to graph that? No. I was just trying to help make the point that, yeah, absolutely. Sometimes we're going to evaluate an integral using the fundamental theorem of calculus and get a value of 0. And it probably means that if we looked at the graph, the areas on the top and the areas on the bottom would all cancel out. Okay, I promised I'd save time for homework. What do you have for me? And I suppose I should go pull up the homework. Everyone's good? Oh, yeah. Homework. Okay. Homework 3, 2a. Oh yeah, hey, look, it's got that 2 over t function. So I am looking at dy dt, and you that is not in focus at all. That's cool. Sweet. Okay. And if I am writing down the wrong problem, always you are free to please tell me. Does that look like the one we're looking for? Okay, sweet. So this part right here is only going to come into play in a second. There's a reason I needed t to be not equal to 0. Why can't t be equal to 0? Right. So if I can't divide by 0, the only purpose this serves is to let you know, hey, don't worry about it. We're not going to accidentally divide by 0. Finding that antiderivative of 1 is going to be t, because we're asking ourselves whose derivative is that? And whose derivative is 2 over t? That's the 2 ln t we had, same 2 ln t we had before, plus some sort of constant. Notation-wise, this tells me that when t equals 1, y is equal to 5. And that's enough to allow us to solve for t. So did I make a mistake?
Oh, no.
Yeah.
So because the t is already said that it's greater than 0, you don't have to worry about that.
That is accurate. Did everybody catch that? So you could choose to be safe and always put the absolute value on t. The fact that this told us t was greater than 0, I didn't have to put the absolute value there because I already knew it was bigger than 0, so nothing bad was going to happen. My domains were already going to match. But it is completely true and correct to always put the absolute value on there, and that's fine. There are going to be some cases where we have to actually figure out whether it was going to be positive or negative. But in this case, didn't have to worry about it. So now I'm going to plug in the 1 for t. Natural log of 1 is a number we're supposed to know. Natural log of 1 is 0. Which means I've got 5 is equal to 1 plus 0 plus c. And c is going to have to be 4. So my final answer would look like y is equal to t plus 2 ln absolute value of t if you want, plus 4. Also, some people like to use something to check your answers, whether that's like Symbol Lab or Wolfram Alpha or any number of other things, photo math, right? Lots of options out there to check your work. That's definitely not what it's going to say. This is correct. And also, I happen to know because I tried this yesterday. That's the answer that pops out of Symbol Lab. They're equivalent because anytime I've got a number out in front of a natural log, I can use a natural log rule to pop that 2 in. So just be careful if you're checking your answers with other things. Sometimes you have the right answer and I see people freak out thinking that they did something wrong. Actually, it's just some sort of algebra sitting between you and what the solution looked like. More questions? Yeah. Sure. Loading. 1H. Oh yeah, totally. Fun with trig. Okay. So here we've got a definite integral from 0 to pi over 3. And what we have here is sine of x plus sine of x tangent squared x whole thing over secant squared x dx. I am definitely not looking at that and knowing who the heck, I don't know whose derivative that is. That is some trash. Not really. So I'm going to do something to help it look better. And the first thing that I'm going to do is go, I don't want to play with secant. So I am instead going to note that 1 over secant of x is the same thing as cosine of x. Other things I know, in case it's helpful, I don't know if it will be, but tangent of x is sine of x divided by cosine of x. And my hope is that armed with those two things, we can make this look a whole heck of a lot better. Let's find out. Again, I'm not finding the antiderivative yet. I'm just trying to find ways to rewrite it. So I'm going to take that secant squared on the bottom, and I'm going to turn that into a cosine squared on the top. So I would have a sine of x times a cosine squared x plus a sine of x times a tangent squared x times a cosine squared x. That whole thing was just dealing with the secant squared part. But I think it's also going to be helpful if I replace the tangent squared. So I'd have sine of x cosine squared x plus sine of x, and then sine of x over cosine of x, whole thing squared, and then cosine squared x. Good news. Nice things are about to happen. Whole lot of work, but two nice things just showed up for us. The first nice thing that showed up is that cosine squared x cancels with that cosine squared x. The next nice thing that showed up for us, if you took calculus in a previous life and you know things about antiderivatives, your brain may have gone in a different direction. At this point in the quarter, we're not supposed to know anything fancy with antiderivatives. And if I'm not supposed to know anything fancy with antiderivatives, there must be some algebra way out of this. And the algebra way out of this is that I can factor a sine of x out. If I factor that sine of x out of both pieces, when I pull it out of the first chunk, I'm left with cosine squared x. And when I pull it out of the second chunk, I'm left with sine squared x. This one you are expected to recognize, know, have memorized. Cosine squared x plus sine squared x. What's that equal to? Show me on your fingers what that's equal to. That's your hint. It's a number. It's 1. And that you are expected to have memorized and know. Which means all of that whole thing is really just find the antiderivative of sine of x and evaluate it at pi over 3 and 0. Whose derivative is equal to sine of x? Negative cosine. And then we're evaluating that at 0 and pi over 3. So I'd end up with negative cosine of pi over 3 minus negative cosine of 0. I think we ought to be able to simplify both of those, but I'm sure it would be fine to leave it as well. If I was trying to evaluate cosine of pi over 3, by the way, I would go to my handy equilateral triangle, cut it in half, and know that that was a pi over 3. So cosine of pi over 3 is 1/2, and cosine of 0 is 1. So I'd have negative 1/2 plus a 1 for a final answer of 1/2. Yeah.
Could you explain how you got the second cosine squared?
So, so this one and this one are from converting the secant squared.
Oh, okay, so
And then this one and that sine squared x are from dealing with tangent.
so secant squared x distributes into 2 cosine squared.
So the secant square, so because it was underneath, I think I wrote the problem right. I'm sure I did because it worked out so nicely. That secant squared belongs to everything in the numerator. So that plus sign lets me break this apart as the first piece, the sine over secant squared, and then the second piece, the sine x tan squared x over secant squared. And I'm just converting that over secant squared to instead be a times cosine squared.
Oh, so like that would be the same thing, like separating the denominator first and then converting it into.
Yep. Yeah, so if you did an extra step of writing that as 2 separate fractions first and then converting, totally equivalent. Yep.
And then we also do J.
Yeah, I think we got time to do J. Oh, for sure we have time to do J. And we should do J. If you haven't figured it out yet, calculus instructors seem to really like absolute values. So genuinely, I think the easiest way to evaluate this is to draw a picture and find areas of triangles. But if I'm going to do this as a calculus problem, then when I see absolute value, I have to think about it as a piecewise function. So the absolute value of 2x minus 1 as a piecewise function is 2x minus 1 as long as what's inside is a positive number. And what's inside is a positive number if x is greater than or equal to 1/2. And it's negative 2x minus 1 if x is less than 1/2. So if I'm going to do this as a calculus problem, I have to take this and break it up into 2 parts. I need to have the portion that goes from 0 to 1/2, where the function is just 2x minus 1. And then I need the portion that goes from 1/2 to 2. And on that portion, I have to use the negative of 2x minus 1 as my function. 2 definite integrals for the price of 1. Now you would just find the antiderivative for each of those, plug in the endpoints, subtract things.